right, thank you for the introduction. Hi, everyone. My name is Ashley. I'm super excited to be here at Canvas speaking for the first time. Today, I want to talk to everyone about our work on improving accuracy and consistency in real-world cybersecurity AI systems via test-time compute. And this is a joint work with my co-authors, Chen, Shawn Davis, who are in the audience today, and also Dhruv Nandakumar, who couldn't be here with us today. I need this. So for today's agenda, we'll start with some introduction and motivation for AI agents in cybersecurity and their associated accuracy and consistency challenge. I'll go over some background on test-time compute and share the specific test-time compute experiments that we ran. I'll share some key results and discussions, and we'll end with conclusions and ideas for future directions. So we're going to pivot a little bit from deep reinforcement learning agents and talk about LLM agents. So I think most of us in this audience are probably familiar with LLM agents and their usefulness in cybersecurity defense. So I'll just give a super brief introduction. LLM agents are autonomous systems powered by LLMs that can reason, plan, and act through tool use, data integration, and memory. And this allows them to orchestrate multi-step workflows and integrate with enterprise systems, which is very valuable and promising in cybersecurity. And because of these capabilities and promise, many cybersecurity organizations are increasingly looking to adopt agents to streamline their cybersecurity workflows. And so speaking of adoption, we've been experimenting with a lot of different cybersecurity agents at NVIDIA across a variety of different use cases. And today, I just want to introduce two specific agents that we'll focus on in this talk. So the first one is a vulnerability analysis agent. This agent is responsible for analyzing the exploitability of vulnerabilities that are detected in software containers. And the goal of this is to help prioritize the vulnerabilities that are highest risks before a software release. So at a high level, this is a event-driven system that is plan and execute style agentic workflow. We start with a vulnerability scan result from a traditional container scan. And this agent, given information about the vulnerability and container, will generate an execution plan of steps that the agent should take to understand if the vulnerability is actually exploitable in the container. Then it kicks off a bunch of React agents to go investigate the plan. And then next, it summarizes the investigations and categorizes them into an exploitability status. Finally, it generates a report for a human analyst to review. Next, we have the alert triage agent, which investigates the root cause of host monitoring alerts. And this is also an event-driven system. But unlike the vulnerability analysis agent, it's a hierarchical multi-agent system that consists of a core tool calling agent that has access to a variety of diagnostic tools and also can call a specialized data analysis sub-agent for deeper telemetry analysis. So given the alert, it categorizes it into an alert root cause and also generates a report for analysts to review. Although these two systems have very different architectures, they have two design patterns in common. One is that they're both classification-based, which allows us to evaluate the system using traditional labeled data sets, which is very helpful. Another common design pattern is that they both generate detailed reports that contain helpful information, such as detailed investigations by the agent, detailed intermediate steps from the agent, investigation summaries, and actionable guidance, which we've found to be very, very helpful for our analysts to support their decision-making. So we've only given a very brief introduction to these agents, but they're both available on GitHub if anyone is interested in learning more about them. Okay, so both of these agents are actually examples of real-world agents that we're actively testing at NVIDIA. And one of the challenges that we faced in trying to deploy these and grow their adoption is we found that it's really important for our agents to be correct and reliable, for them to be trustworthy agents in production, especially in a high-stakes domain like cybersecurity. So next, I want to hone in specifically on the accuracy and consistency challenge. So for cybersecurity agents to be successful and trusted in production, we need both accuracy and accuracy, which is how correct the system is, and consistency, which is how stable the outputs are for the same input across multiple runs. However, one major challenge for agentic systems is the non-determinism of LLMs. Which is because LLMs are probabilistic by nature, so the outputs can vary from run to run, and any variance can really propagate throughout your agentic systems across multiple LLM calls and cause divergent reasoning paths and contradictory conclusions, which can be very challenging and problematic for trustworthy agentic systems. So because this is such an important problem, we're always on the lookout for various ways to improve our agentic systems performance. And we're especially interested in easy and practical methods that can improve the performance in terms of accuracy and consistency without actually expensive retraining or re-architecting the agentic system. And so this brings us to test-time compute. Test-time compute has recently become a key technique for advancing the state-of-the-art in LLM capabilities. So it caught our attention as a really promising solution. First of all, what is test-time compute, in case you haven't heard of it? It improves model performance by allocating extra computation during inference time instead of at training time. So this enhances the accuracy and reliability of your model without your system without retraining the LLM or changing the agent architecture. So here I just want to share some general patterns for test-time compute techniques that, for the sake of this talk, fall under these 4 patterns. So the first is aggregate, where you generate multiple results and either merge them or aggregate them in some other way. The next is search, where we iteratively search through diverse reasoning paths to find an optimal solution. Next, we have verify, where we add a verification step to improve the generated output results. And finally, we have reason, which, like reasoning models, uses extra chain of thought tokens to improve the response. So there's a lot of research out there already and real-world examples that show that test-time compute is highly effective. But when we were looking into test-time compute and looking for literature, we found that it's actually relatively underexplored in cybersecurity. And so we were interested in seeing which of these design patterns and, are really effective and test them on our 2 real-world agents. So to understand which test-time compute techniques are most effective, we ran a variety of different experiments using various test-time compute methods. This slide shows an overview of the 3 different types of experiments that we ran, which we'll discuss more in detail in the upcoming slides. But the first type of experiment we looked at was system-level test-time compute, which is, can we simply just execute our full agent workflow multiple times and vote on the results to improve accuracy and consistency? The next bucket of techniques that we looked at was component-level test-time compute. The idea is that, can we apply test-time compute on specific components in our workflow to be just as effective as system level while improving the efficiency? And lastly, this isn't a test-time compute technique, but we were curious about whether if you're going to be running your workflow multiple times, can we calculate distributional scores across all your different workflow runs to generate a confidence score? And is that going to be predictive of your agent accuracy, which would be very useful. So a little bit about the implementation details of our experiments. We did have labeled data sets around 45 and 46 examples each. And specifically, we curated these data sets so that they would be challenging, so that our agents avoid hitting a performance ceiling. And in terms of agent implementations, we used LangChain and LangGraph. And also, I wanted to introduce a toolkit that we used called the NVIDIA NeMo Agent Toolkit, which is an open source framework agnostic library for profiling, evaluation, and optimization of agent AI systems. And we found this really helpful because it provides a variety of different tools for practitioners to make agent development easier. And speaking of one of these tools, it actually has a test time compute module built in, which we found was very helpful for enabling quick experimentation because it has pre-built test time compute functions and also allows us to write custom strategies as well. So this is available on GitHub as well if you're interested in taking a look. Okay, so let's dig into the results, probably the most exciting part. The first set of experiments we ran was the system level test time compute. And so this was majority voting in the vulnerability analysis agent. So for this experiment, quite simple, we just repeated the workflow execution multiple times and took a vote on the output. There were 3 variations of this that we looked at. Simple majority voting just takes the most frequent label. Decisive majority voting penalizes unknown labels, and this helps match real-world label distribution, which has less unknowns than what the agent naturally generates. And we also looked at early stopping, which halts your executions after 3 consistent labels so that you can reduce your cost. For each of these experiments, we ran the majority voting for a number of executions from 3 to 10, and then we looked at the accuracy on our labeled test set. And we actually repeated these experiments multiple times so that we can look at a distribution of the accuracy score on our labeled data set. So that allows us to look at the mean and the standard deviation of the accuracy across multiple runs. So the outcome here is that we found majority voting improved both accuracy and consistency, with the best results coming from the decisive voting variation. So if you take a look at the plot on the left, we have in the blue line mean accuracy, and in the red line standard deviation of your accuracy. So you see your mean accuracy improve from 63% to 76% after 10 votes, and accuracy standard deviation reduced by 42%, which is almost reduced by half. So we were pleasantly surprised at how well this simple technique worked out. But we did want to call out that even though it's simple, it does come with a trade-off, which is that if you run your workflow 10 times, it comes with a 10 times cost. And so because of the cost trade-off, when does this technique really make sense? And I think this really depends on your use case. So for use cases that have really low error tolerance, every bit of accuracy helps. And so this technique will be very helpful in that scenario. And we think that this is especially true in cybersecurity. And the next thing is that we wanted to just give a couple of practical tips, which is that ideally you'll want to select the number of executions that optimize the trade-off based on your business requirements and experimentation. And also that early stopping is a helpful mitigation for cost, since it reduces cost by 43% while maintaining most of the accuracy that you get from the best technique. For the next experiment, we essentially repeated the previous experiment, but on the alert triage agent, and we saw a really similar outcome. with the mean accuracy improving from 75% to 80% across 10 runs, and accuracy standard deviation dropping by 31%. And so this led to our conclusion that majority voting is consistently effective across agents with different architectures. So next, that brings us to our component level test time compute experiments. So this is an older experiment that we ran when DeepSeek R1 first came out and took the world by storm. We wanted to see if just directly replacing our existing LLM model with a reasoning model could boost performance. Unfortunately, spoiler alert, we found that the results were sort of mixed and not really worth the trade-offs, which were that replacing all the calls increased our execution time by 8x, which greatly increases the latency. And also, without any other adjustments to like hyperparameters or prompts, it dropped the accuracy to as low as 47%. Tuning hyperparameters did raise the accuracy back up, but we saw variability also increase by 20%. This led to our observation, which is that reasoning models are not really a simple drop-in improvement, but require prompt tuning or architectural changes to be effective. Even though we only show results for DeepSeek R1 here, we later repeated a similar exercise with GPT-OSS and found a similar finding. Our next component level test time compute experiment that we ran was execution plan merging. So for this one, we generated multiple execution plans and merged them using an LLM prompt. So here on the left, we can see various different prompts that we tested. And the outcome was that for our best prompt, it improved consistency by a little bit, as shown in the red line decreasing a little bit, but there was no meaningful improvement in accuracy. Our key finding here was that prompt design is critical, since if you look at the middle here, a naive merge prompt where we didn't do any prompt engineering at all tanked the accuracy to pretty much 0. One other component level test time compute experiment that we ran was adding a self-reflection prompt in the alert triage agent to critique and revise the root cause classification. And this did lead to a small accuracy increase, but it took a lot of prompt engineering to get here, and it still wasn't as effective as just 3 runs of majority voting. So this doesn't mean that self-reflection is not effective. Our hypothesis is that it may be more useful in more open-ended tasks compared to root cause classification, which is a simpler task. And lastly, that brings us to confidence scores. So we derived various confidence scores from distributional metrics from running test time compute, and we measured the correlation with the accuracy label. And we were disappointed to find that none of the evaluated metrics were really strong predictors of accuracy. So we looked at majority voting share, which is the share of votes in your majority voting runs that matched the actual majority. And this had only a weak positive correlation with correctness, as we can see in the plot on the left. And we saw a similar pattern with other metrics like runs until convergence and tool call stability across runs. So we found that these distributional signals, at least the ones that we came up with, were not really reliable for confidence scoring. Okay, taking a look at some discussions and key takeaways across our experiments, we found that system-level test time compute provided meaningful gains in both accuracy and consistency across both agents, and they were very easy to apply, requiring minimal architectural changes and tuning to be effective, but at a trade-off of higher inference cost. Of these techniques, majority voting with early stopping stands out as the technique with the best cost to benefit trade-off. So we give that one a thumbs up. For component level test time compute techniques, these were less effective in our particular experiments, but this doesn't mean that they're not effective in general. It just means that they require a little bit more careful application, especially trying to figure out which techniques to apply in which components in order to be successful. So this is definitely an area for future research. And lastly, confidence scores. We were a little bit disappointed that despite how intuitive they seemed, they were pretty elusive for predicting accuracy. So this is also another area for future research. In terms of conclusions and future directions, what do we want everyone to walk away with and take home? First is that both accuracy and consistency are critical for agent reliability in a high-stakes domain like cybersecurity. And specifically, I wanted to call out consistency, which might be overlooked oftentimes. Next, test time compute, and especially majority voting, is a practical tool that we as practitioners can add to our toolbox for boosting accuracy and consistency in cybersecurity without model training or architectural changes. And this is especially effective after you've exhausted other techniques like prompt engineering and hyperparameter tuning to squeeze out some extra performance. And lastly, we did want to call out that even though agents sometimes don't give perfect results, they still do provide value in cybersecurity through automation. And as we discussed earlier with the reports that we generate, they're helpful through their intermediate results, summaries, and actionable guidance. And in terms of future directions, we want to further explore different test time compute techniques. So going deeper and extending our existing experiments and exploring additional strategies such as adaptive search and self-evaluation with verifier models. We're also interested in looking at alternative models. So can we use, does test time compute allow us to switch to smaller models? We want to look at newer reasoning models. And also, we're interested in looking at cybersecurity specific models, such as the Foundation Security 8B reasoning model developed by Cisco. And lastly, better confidence scores. Although none of the confidence scores that we tried worked out, we still think that this is an important research area towards our goal of more reliable and trustworthy agentic systems in cybersecurity. And with that, that concludes my talk. Here is a slide on where you can learn more about the agents and the Nemo Agent Toolkit that I mentioned in the talk. And I believe these will be posted to the Canvas website afterwards as well. So as I mentioned, everything's available on GitHub, and we welcome any questions or contributions.
Excellent. All right, questions? Yeah, let's see first. Or Rich first.
So, hi. The bagging ensemble classifier you did, majority voting, did you use the same prompt every single time, or did you diversify prompts to try to diversify the output?
That's a great question. We use the same prompt every time and same hyperparameters, actually. And this is because of the inherent non-determinism of the specific LLM that we were using, which was Llama 3170B. We found that even with a very low temperature, same prompt, same hyperparameter, we got wildly different results that cascaded throughout the system. And so this left enough natural diversity for us to get good results from majority voting. I think it would be really interesting to look at what happens if you do vary the prompt or hyperparameters to get even more variability. But I don't have results for that off the top of my head.
Yeah, one of the standard things you try to do when you're bagging classifiers is uncorrelated.
Yeah.
Cool result.
Yeah, absolutely. I totally agree. Yeah.
Thank you. That was super interesting. I had a question about the reasoning substitution. If I understand correctly, you changed two things, right? You switched between models and then you enabled reasoning because DeepSeek is a reasoning model. So I wonder if you explored a substitution where you keep the same model. Let's say it's a reasoning model, but you disable its reasoning so the model stays the same.
That's a great question. We haven't tried it. I know there are models out there that do enable reasoning on and off, so that would be interesting to look at as well. I think at the time we were very curious about the capabilities of reasoning specifically, so that's why we looked at that model. But yeah, that would be an interesting extension as well. Yeah.
Great talk. So the thing that came to mind, and I don't know much about test time compute, but instead of doing voting on the outputs, you could take all the outputs plus any intermediate outputs and so on, any other information or explanations that might be available, take them all, feed them into basically another round of LLM, right? And do reasoning over all of those outputs and then use that to make a decision. Is that something you've looked into?
Looked into that, but I think that's a great idea, and I think it really does fall under example of test time compute as well, because not only are you generating multiple runs, but you're also using another LLM to sort of like judge and aggregate. I think that's also similar to sort of our execution plan aggregation step, where we generated multiple execution plans and merged them. So I think it's like a hybrid of the two techniques, right? So yeah, that would be.
Just